This chart shows the standard electromagnetic spectrum, mapping propagating waves from low-frequency radio on the left to high-frequency gamma rays on the right. While instruments have limits, classical electrodynamics theoretically allows the spectrum to extend infinitely, shrinking the wavelength toward zero without end. But physical reality does not permit zero-wavelength propagation. At extreme energies, the standard model of continuous waves fails. This breakdown occurs because the universe possesses an ultimate theoretical boundary to its geometry, the Planck length. This is a distance of 1.616 times 10 to the negative 35th meters. Beyond the regime of hard gamma rays, the foundational environment required for a continuous electromagnetic wave degrades and ceases to exist. The driver for this limit is the Planck-Einstein relation. This equation defines a photon's energy as Planck's constant times the speed of light, divided by its wavelength. Because wavelength is in the denominator, scaling it down toward the Planck limit causes the required energy to spike exponentially toward 10 to the 19th giga-electron-volts. At these levels, the classical wave description diverges from the physical reality of individual interactions. The energy concentration becomes high enough that the smooth sine wave no longer accurately predicts the outcome of a photon's travel. These mathematical extremes mark the transition from Maxwell's continuous fields to the discrete, localized events modeled in quantum electrodynamics. We can anchor this transition in current observational astrophysics, where we detect ultra-high energy cosmic events. Specialized water Cherenkov arrays like the HAW Observatory use massive tanks of purified water to capture the signatures of incoming gamma rays exceeding 100 tera-electron-volts. At this energy level, standard wave-based optics and radio antennas are ineffective. The radiation does not induce a clean current in a conductor or reflect off a mirrored surface in a predictable wave-like pattern. Instead, these high-energy photons strike the upper atmosphere and immediately generate cascades of secondary particles. At these observational limits, the wave model is practically obsolete. The propagating photon behaves entirely as a high-energy interacting particle. In this regime, quantum electrodynamic interactions dominate, specifically pair production and Compton scattering. Modeling light at these scales requires tracking the discrete quantum interactions between high-energy photons and electrons. In the pair production mechanism, the photon's energy is entirely converted into mass, resulting in an electron-positron pair. This replaces Maxwell's continuous fields with the probabilistic particle exchanges defined by QED. As photon energy scales upward, standard wave propagation terminates, replaced by the conversion of energy directly into new pairs of matter. If we push the scale 15 orders of magnitude beyond current observations, we reach the Planck energy of 1.22 times 10 to the 19th giga-electron-volts. Calculating the absolute limit of space requires a specific derivation for the Planck length, utilizing Planck's constant, the speed of light, and the gravitational constant, g. The inclusion of gravity here is significant. Usually, gravitational effects are too weak to matter in quantum mechanical calculations. But at the Planck energy, the photon's localized energy density is so massive that its gravitational influence equals its quantum effects. This intersection marks the theoretical wall where gravity must be integrated into quantum calculations, a process that breaks standard QED. To see why the wave model fails, we have to look at the theorized geometry of spacetime at 10 to the negative 35th meters. At this scale, spacetime is theorized as a quantum foam, a granular and violently fluctuating geometric field. An electromagnetic wave requires a specific physical prerequisite, a continuous, smooth spacetime manifold to propagate through. The smooth geometry required for wave propagation is absent here. A wave cannot maintain its structure across these disjointed gaps. When the distance between two theoretical wave peaks is shorter than the smallest measurable unit of distance, the physical property of wavelength ceases to exist. Pulling back from the Planck scale, we can view the entirety of the electromagnetic spectrum as a finite phenomenon. This upper limit forces a re-evaluation of the lower bound as frequency approaches 0 Hz. At the lowest frequencies, propagating waves similarly hand off to static fields and magneto-hydrodynamic phenomenon. This creates a low-energy boundary that mirrors the high-energy, short wavelength limit found at the Planck length. The electromagnetic spectrum exists as a finite physical domain, defined on both ends by the specific geometry and limits of our universe. Currently, there is a massive gap between our observational tools and the theoretical threshold of the Planck energy. No particle accelerator in existence, or currently planned, can achieve the 10 to the 19th giga-electron volts required to reach this limit. Bridging this gap requires theoretical frameworks like string theory or loop quantum gravity. At the Planck limit, both general relativity and quantum mechanics fail to provide a complete description of reality. Past the Planck scale, light is no longer light. The electromagnetic spectrum terminates, handing its domain off to the unsolved physics of quantum gravity.